Thanks, Tori. Hi, everybody. Thanks for taking time out from your day to do this. As Tori said, we're going to focus on the airtightness testing requirements for the new commercial energy code. Before we do that, just a couple quick comments about the intended audience here. We've kind of designed this for folks who already know how to do blower door tests, or at least understand enough about them to know what the units of measure are and that sort of thing. So we're going to focus mostly on the differences between testing single family homes and testing commercial buildings. And before we go there, just a couple quick comments on why this stuff is important. If we could go to the next slide. The code is very concerned with airtightness because it's really important in the performance of buildings. And a lot of us think of it as primarily an energy efficiency thing, but it's not really. There's a whole lot of other advantages to building airtight. You can kind of see some of those here. Better control of a whole variety of things that come and go in and out of the building, not just cold air, but humidity and pests and critters and smoke from fires and odors from the downstairs neighbor's dinner and all of those things. So especially in commercial buildings, airtightness is really important, and it tends to be one of the most cost-effective things that we can do to keep energy bills low, protect the building from moisture problems, and make it durable. And I don't think we need to say anything more about that because hopefully you're all on board with believing that airtightness is a good thing. So with that, I'm going to turn it over to Charlie, who's going to talk about the new commercial code requirements.
All right, can you all hear me?
Yep.
Okay, great. Yeah, my name is Charlie Carpenter, and I will quickly go over what the new 2020 Commercial Building Energy Standards requirements are for blower door and air sealing. How that compares to the current 2015 code. So in red there, the biggest difference with the upcoming 2020 code, which will be effective September 20th of 2020, will be that blower door testing will be required on all new buildings and additions. And there are two different ways that you can comply with this. One is doing performance testing, which is a blower door test, and you need to hit an actual CFM per square foot value, which I will get to later on. The second option is to do a more detailed air barrier commissioning process where you have a checklist and a report that's generated. There's no test number that you need to hit there, but there is likely a lot more work to make that possible. So a majority of buildings are just going to test and see if they can hit the performance requirements. Next slide. So for the blower door air barrier performance testing, the value that needs to be hit in the new version of the code will be 0.30 CFM per square foot of envelope. The current code is 0.50 CFM per square foot. So it has gotten a bit tighter there. The other large change is that this new test will be using the six-sided envelope of the building. That means that the slab and below grade walls will now be included in the calculation. The current code is only doing five-sided, where anything below the grade is not included in that calculation. And lastly, the depressurization is being increased from 50 pascals up to 75 pascals for the entire test. There are a few exceptions. If you've got a large building that is 50,000 square feet or more, you can test a portion of the building, and there are certain areas that you do need to hit, like the top level of the building, the entrance, or any areas where you have loading docks and a lot of overhead doors. And you also must measure 25% of the wall area for the building. And if you test a building and the results are between 0.3 CFM per square foot and 0.4 CFM per square foot, then what you need to do is find the leaks in the building while it's depressurized, and you don't need to deconstruct anything, but you need to seal up whatever leaks you can, and you need to write a report, document what you did and what the changes were, and send that to the owner. That's it. Next slide. So if you go with the second option, where you don't just want to hit one number and be finished with it, you can do continuous air barrier commissioning, where it's pretty detailed. There's a field inspection checklist that I'll show on the next slide that you need to follow all the steps in that during the construction. And there's also a report on how you're handling and storing your materials and prepping surfaces before you're applying all the different materials that make up the air barrier of your building. And this report will be sent to the owner or owner's rep once it's completed to keep on file. Next slide. So this, I'm not going to go through all of this, but this is a screenshot of the envelope commissioning checklist that is in the code, and all the different components of the assembly for the air barrier and what you need to check for those portions of the air barrier and put that in the report. So as you can see, there's a lot of detail in here. So I think most people will just be doing the first step where you test the building and try to hit the performance number. Next slide. The last portion that was changed in the code for the 2020 version is dwelling unit air infiltration testing. So if you have a building that either is mixed use or multifamily with a good number of dwelling units in it, there needs to be a random sampling of each unit that is tested on its own without adjacent units. So 10% of the units in each building should be tested. You have to at least do a corner unit, one per floor, and try to do about equal numbers of units per floor. And each individual dwelling unit needs to meet 0.35 CFM per square foot. And that will also be depressurized to 75 pascals. And you're obviously using the 6 sides of that dwelling unit for the surface area calculation. Next slide. And each of those units that is tested must pass in order to meet the energy code. You can't have one unit that doesn't meet it. Every single one needs to. So if one of those units fails, you need to find, while it's depressurized, you need to find the cause of the leaks, and you need to fix those leaks, seal them up, and keep retesting the unit and fixing leaks as you find them until that unit passes the requirement. And the units that are selected will be at random. The contractor can't specify which ones will be tested by the contractor. So day of the test, you just kind of randomly select units that meet the criteria of the previous slides. And during the test, the HVAC systems will be shut off, but there will not be any wrapping of HVAC, dampers and diffusers and exhaust grills or makeup air or anything like that. So just with the natural dampers that are built into the HVAC system while it's shut off. And that is all I have. So I will pass it back to Dave to talk about blower doors in larger commercial buildings.
Thanks, Charlie. So as I said, this is kind of intended for folks who already know something about blower doors. So we're going to focus on the differences between testing in single family and testing in commercial buildings. If we could go to the next slide. So compared to houses, you've got more limitations on scheduling and access because you've got more people coming and going. Some of them have schedules that can't really be altered. Everybody who works in the building is going to feel that their schedule is more important than yours. So often we are doing tests on, not times and dates that we might prefer, but when the building is available. Everything takes longer, everything is further away. So if you have to, if you forget something and have to walk from the boiler room to the attic hatch, that's a 50 or a 60-foot walk in a typical single family residence, but it might be a 2,000-foot walk in a large commercial building. So it's good to be organized. It's good not to have to visit the same location 3 times because it takes 10 minutes to get there and back. There's more HVAC equipment in larger buildings in general. It tends to be more complex, harder to understand. We need to have things shut off for the test, just like in single family, but shutting off the heating system in a single family residence is pretty simple compared to shutting down all the space conditioning and the ventilation equipment in a big building. So we've got more equipment to deal with. For some of the testing we do in big buildings, we end up masking off a lot of stuff. That's not the case with code. So if you're thinking about you're going to be doing blower door testing for code compliance, you're not going to do a lot of masking. That protocol does not involve sealing much stuff off. But there are other protocols separate from the code that do involve a lot of masking. So depending on who you're working for, whether it's new or existing, and what kind of information you're supposed to collect, in a lot of these tests, a good deal of the time setting up the building is taping things off. You got more complications with occupants and security. As I said, you got people coming and going. You can't really control that. People will come and go through doorways, even though you just told them 5 minutes ago that it's really important that they leave the door closed. They'll do it anyway. There are security issues. So, for instance, and you may not run into as much security issues in code compliance testing because, for the most part, these buildings will probably be empty. But once you start doing occupied buildings, you got to think about things like, if you've got 50 apartments that all open onto central hallways, and you're going to need the doors to those apartments open for an hour or more while you do all your testing, the occupants are not going to like that idea of their apartment door being open for an hour so anybody can stroll in and out. So sometimes you end up literally hiring security to stand in the hallway and guard everybody's stuff. You'll probably need a facilities person. You'll need somebody who has keys to everything, who understands how the mechanical equipment works, who's familiar with the building. And again, that's different than single family. Most of us could go into a single family residence by ourselves with nobody there and we'd figure it out. But in a larger building with more complicated equipment and also harder access, you've got more things that are locked. You've got more utility rooms and storage spaces and that sort of thing that you might not even know they exist unless you've got somebody who's familiar with the building. Larger buildings more likely to have multiple zones that you don't know how much they connect. They may be connected to other buildings. And often in this larger building test, we're looking at more detailed documentation, not just a single number, but also a description of the configuration of the building, whether things were on or off, what doors were open, what doors were closed, what doors had blower doors in them, etc. Next slide, please. So a quick review of the units of measure. So sometimes we describe the airflow in a building, and we describe just the airflow at a specified pressure. So that's CFM 50 or CFM 75. Sometimes we describe the leakage by describing a hole that is meant to approximate how much leakage we have. Most of us don't use this very much, but it is out there, and some people find it useful to describe how leaky a house is to homeowners. So for instance, right now, all the holes in your house would add up to the hole the size of a basketball, and we're going to bring it down to the size of a baseball. So some folks think that's a useful way of describing things. It doesn't really enter directly into any of our calculations usually. And notice that the effective leakage area and the equivalent leakage area are measured at 2 different pressures, and that's why those 2 numbers are often very different from each other. Often the equivalent leakage area is twice as big as the effective leakage area. Another way we could describe the leakage of a building is to compare the airflow to the volume of the building. And for that, we use a unit of measure called air changes per hour at 50 pascals, or perhaps air changes per hour at 75. That has been the standard way of comparing buildings of different sizes historically. We would compare them according to how much they leaked compared to their volume. It's not the best way to do it, and the industry is headed in a different direction. And eventually we will probably be doing all of this by normalizing to surface area rather than to volume. But in the meantime, we're going to continue to see both numbers. So for instance, the residential energy code goes according to volume and requires the house not leak more than 3 ACH 50. But as Charlie pointed out, the commercial code deals with surface area. So that's the last unit of measure on this slide, airflow at a test pressure divided by the enclosure surface area. This is a better way to compare buildings of different sizes. When you compare volume, the big buildings tend to look better. It's just a matter of geometry. As the same shape gets bigger, the volume it encloses increases faster than the surface area does. It's just math and geometry, just the way the world works. So if two buildings are built exactly the same materials, put together exactly the same, but one is bigger, the bigger one will look better if we use ACH 50. But buildings don't leak according to volume, they leak according to surface area. So it's better to say, this is how much leakage we want per square foot of enclosure or per 100 square feet of enclosure. So that's the last one. The only iffy part on that is, are we talking 5 sides or 6 sides? Are we talking above grade only, or are we talking total surface area? And I think we have industry consensus that the most sensible thing to do is to consider all 6 sides with no consideration of what's above grade or below grade. In fact, the below grade stuff can leak and often does. And also, 2 people looking at the same building might come up with different numbers for how much is above grade and how much is below grade. So this takes that kind of judgment call out. So I think going forward, even though in the short term we'll continue to see air changes per hour, going forward we're going to see more CFM per square foot of envelope, and it will be 6 sides. Next slide, please. I think it's useful before we do a test to ask, what question is it we're trying to answer? Now we're focusing today on code compliance, and so we're mostly focused on, that's essentially the question that we have to answer. But in a more broad general sense, as we test buildings, we are asking different questions of different buildings, and it does make a difference in how we test. So in some cases, this is a pass-fail according to some specific standard, and that's what we're talking about here today. The standard in this case would be the energy code. So that's a pass-fail. You need to be accurate enough to know what side of the line you're on. Sometimes we just want to get a general sense of how leaky the building is, what is the magnitude, how big is the opportunity to change things, how bad are things there. In that case also, we might not necessarily need a high degree of accuracy, but we do need to get a general sense. Sometimes we're testing according to our strategy of just, we don't really care very much what the number is. What we want to know is where the leaks are. That makes a difference. If you want to get a really accurate number at 50 pascals, you've got to be at 50 pascals or close to it. But you can identify leaks in the building at 10 pascals. So that may make a difference in terms of how you approach the diagnostics and how much equipment you have to bring along. And then, of course, sometimes we test before and after to determine how much of a difference we make. That's pretty common. We do that all as standard procedure in the home performance program. I'll just throw in one quick comment that if you're not correcting for outside temperature at the time of the test, those before and after numbers, that comparison may not be terribly accurate, at least in some houses. Next slide, please. Lots of different ways to test. Most of us learned single point tests. Not me. Back in the 80s when we were getting started on this, we were all doing multi-point tests. So we wouldn't just do a single measurement at 50 pascals. We do a measurement at 50 and one at 40 and one at 30 and one at 20 and one at 10 and average them all together, essentially. Most of the time we use negative pressure, depressurization, sucking air through the building to do blower door tests, but we don't have to. We could do positive pressure instead of negative, and some of us occasionally do positive pressure tests for one reason or another. If you get more involved in testing big buildings, you may end up testing to a standard that requires that you test either negative or positive or both. For instance, the Army Corps of Engineers has its own blower door testing standard, and they require that the building be tested under positive pressure and also under negative pressure, and you use the average. Also, we've talked about 50 pascals versus 75. Traditionally, 50 has been the standard for single-family residences and small buildings. I think that will continue to be the case. 75 has pretty much become the standard for commercial testing, and almost all air tightness testing on commercial buildings is now at 75 pascals rather than 50. Not sure of the reason for that. It may have to do with the fact that commercial buildings tend to experience higher pressures under normal conditions, so maybe we test them under higher pressures too. They're taller, so more stack effect, probably more wind effect. They probably have larger mechanical equipment in the building, ventilation equipment and such that may be putting pressures on the building. For us in testing, the main difference between 50 and 75 is that you got to bring like 50% more fans if you actually need to get to 75 rather than needing to get to 50. Most of the time we do a blower door test, we just do a single measurement, but you can repeat. You know, maybe you got a bunch of wind gusts while you did that measurement. No harm in repeating the test. There are also guarded tests where we will manipulate the pressure in bordering zones so that we either, usually we do this to eliminate the leakage between two zones. So perhaps a good example of this would be a duplex. So let's say we are testing one side of a duplex. If we just do that as normal, we're going to have some leakage from the other unit, and whatever blower door number we get will include the leakage from outside and also the leakage from the other unit. Sometimes we don't want to include the leakage from the other unit, and if so, we can deliberately exclude that. And the way you do that is you put another blower door in the other unit and you turn that one on at the same time as the unit you're testing, and you manipulate the pressure in the bordering zone to match the pressure in the zone you're testing. So if the pressure in those two zones is exactly the same, there will be no flow between them, even if there are holes. And your blower door test on the one you're testing will show only leakage from outside. So that's a guarded test, just a way of getting only the leakage from outside without the leakage from inside. Compartmentalized units is a similar but different strategy. In this case, we're trying to see what is the total leakage of an individual unit, regardless of where it's coming from. Could be coming from outdoors, could be coming from the unit next door, could be coming from the hallway, the floor below, the floor above. We're not discriminating between any of those pathways. We're simply measuring what they all are together. And this is what Charlie was talking about when he was talking about the standard for individual units. So the way you would do this is the unit to be tested will have a blower door in it as usual. All the bordering zones that might communicate to that unit need to be opened up to the out of doors and be at the same pressure as outdoors. So you open the hallway to outdoors, you open the bordering units hallway to the outdoors, the floor above open to the outdoors, the floor below open to the outdoors. And conceptually, what we're trying to do is to take this unit and almost as if we were to suspend it in midair with nothing attached to it. That's the idea. And so we're limiting, the code limits the total amount of leakage regardless of where it's coming from. And some folks might say, well, that seems kind of strange, because if the air is coming from the next door unit and it's 70 degrees, it doesn't really affect my heating bill, and that's true. But it has a big effect on noise. It has a big effect on odors. It has a big effect on smoke transmission and fire spread. And it's a really good idea to get individual units just tight to each other. Everything works well. To the extent that you can accomplish sealing off at floor levels, you can take a tall building and reduce the stack effect on it, because the stack effect is dependent upon air traveling freely vertically in the building. And most of you probably know that sealing off the building horizontally and limiting those vertical pathways it makes the building a lot safer in a fire. There's a lot of similarities between fire blocking and air sealing. And then lastly, some of us are doing zonal pressure diagnostics for adjacent spaces, where again, we're paying attention to the pressure in the space next door and how much that pressure changes when we change the pressure in the primary space that we're dealing with. That gives us good information about how much communication there is between those two things, how separated or how connected they are. Next slide, please. So you can do this manually, or you can do it automated. The same is true for single family. So most of us do manual tests most of the time, and you can do that in multifamily too. The difference is you're not doing it by yourself, you're doing it simultaneously with other people. So you need a person to operate each door, and you need some way of communicating, which is probably either a walkie-talkie or a cell phone. Bear in mind that when you are standing at a doorway with your fan, or perhaps your 3 fans maxed out, it's loud, and there can be communication issues just from noise. So that's the manual thing, and basically everybody gets on the walkie-talkies or on a cell phone conference call. One person typically drives the whole thing, so it's important that everybody is taking their baseline at the same time, turning fans on at the same time, reaching the test pressure at the same time, taking our measurements at the same time. So if you're doing it all manually, you need a lot of communication. You can do it automated. And what happens here is, for those of you who haven't messed with this software, the software is free, available from the Energy Conservatory. So you can play with this on your computer, and essentially your computer takes control of the blower doors. It controls the fan speed, it turns things on, turns things off, it does the baseline, does all the measurements. Basically, you just need a human being to set the door up physically and remove rings and that sort of thing, and push play on the computer. So the computer can do all of that. The software is set up to, I could be wrong about this, but I'm pretty sure it will handle at least 8 fans, perhaps more. And you can communicate between your computer and those fans, or you're actually communicating with the gauge that's controlling the fan, with either hard cables, Cat5 cables, like your internet cable, or with wireless. The problem with Cat5 cables is that some of these doors are going to be a long ways away. So you may need a lot of cabling depending on what you're doing in the, how big a building is that you're testing and how far apart everything is. You can do automated with wireless. You need a Wi-Fi equipped gauge. This will have to be, if you're using Energy Conservatory equipment, the Minneapolis equipment, this will either be the Wi-Fi attachment for your DG700 gauge, or the new DG1000 gauge that the Energy Conservatory is selling with the new blower door setups. That's all Wi-Fi enabled within the gauge itself. The Energy Conservatory doesn't sell DG700s anymore, and they also do not sell the Wi-Fi attachment for the 700. So if you don't already have that equipment, you would have to get their new DG1000s in order to communicate wirelessly. The other thing about wireless communication is it is limited. You can have problems in buildings that have a lot of steel and concrete in them. And, commercial buildings tend to have a lot of steel and concrete in them. And so you might need some sort of router booster to put in the building somewhere to boost the signal. Personally speaking, I've not done a lot of this wireless messing around. I think it has lots of potential for the future, and I wouldn't be surprised if we all go there eventually. But right now, if you're going to go that route, you want to play with the equipment and get comfortable with it before you actually show up at the building. One thing to keep in mind when you're testing larger buildings is if you're doing a blower door test on a single family building and you have some kind of problem that holds you up for 20 minutes or whatever, that holds you up for 20 minutes. But when you're doing a big building and you got a 20-minute delay, that's a 20-minute delay for 6 or 8 or 10 people. So it adds up pretty fast. Next slide, please. This is just a look at the TechLog software. We don't have to spend any time on this, but this is just kind of what you end up with. You end up with these lines that show what the pressure and flow was in all of the zones. You can kind of pick what section of data to take your info from. That's what those green boxes are. You can select what they call a period of record. So you can look at, and this is all live on your computer screen, so you can see stuff happening. If something weird happens, like somebody opens a door or somebody turns some equipment on or off, that shows up on the screen. So you can kind of see and get some clues, and also select your information from a period when you can see that the data is good. The other thing is that now you've got a file that has literally thousands and thousands of data points. So you can go back there later on and try to tease some more information out. And if we could go to the next slide, that's just another screenshot of a separate piece of software that this Energy Conservatory sells, but it just give you a quick idea of the kind of info that you end up with. You don't end up with just an airflow at a pressure, but you also end up with a plus or minus percentage and another indicator, the correlation coefficient, which gives you an idea of how accurate the test was. Also demonstrates to anyone who's interested later on that it was an accurate test. You can see your equivalent leakage areas are there, effective leakage area, and a bunch of information that you just don't end up with if you just do a manual test and write down one number on a piece of paper. Next slide, please. So we're going to do a test. We need to know who's involved, how many people we need, who those people are going to be, who is the building rep, who has the keys, who has a knowledge of the equipment. And so when we get there, we have somebody on site that knows how to lock and unlock things, knows how to turn things on, turn things off. You pick a date. As I said, a lot of times we're working around their schedule. Verify the enclosure boundaries, like what surfaces are we testing, or what areas are we including in the test, what areas are we not including in the test. Identify mechanical equipment that we're going to have off, and make a decision on, are there penetrations that we need to be temporarily sealing off with masking material. That makes a fair bit of difference as far as a setup time for the test. As I said, for commercial code, you're generally not going to be masking stuff off. But when you get into testing in existing buildings and troubleshooting, you may well end up doing that. Next slide, please. Who are the people? Does the owner need to be there? Does the building management need to be there? Do you need security there? You're probably going to need to leave some doors open, and you're not going to be there to see whether somebody's going in or out. So you may need to have somebody to do just that. There may be health and safety considerations depending on the building that you're in, or depending on the current status of the coronavirus. You need the team that's going to run the fans, the team that's going to take the measurements. They have to know what they're doing. You have to make sure all their equipment is up to snuff. You need to know ahead of time, are we going to end up spending time looking for holes, or are we just collecting a measurement? That makes a difference. Who is the person who knows the HVAC equipment and can turn things on, turn things off? Occasionally, you may actually have to have a witness, not very often. Probably not in Vermont. We run pretty informally in that regard. But in some cases, you might have to do that. And then fix the holes crew. You may remember that Charlie talked about if you're testing and you come in just barely failing, there's an option for immediately doing some work right then and there to seal those holes up and retest. So if that's your strategy, you have to have those folks and those materials there. On to the next slide. You're going to have to do it when the fewest people are in the building. You know, that's just the nature of the thing. I'm doing one day after tomorrow. We have to arrive at the end of the workday when everybody else is leaving. We've done these tests at 10 o'clock at night. We've done these tests at 3 o'clock in the morning. We've done it at 3 o'clock in the morning on a Sunday morning. Some folks have commercial enterprises that run pretty much 24/7. So, you know, you need to be able to accommodate that. And during the test, you'll need access to everywhere. So any doors that are locked, you know, somebody has to have a key to them, including all the mechanical rooms. And if you're going to have to mask off everything, you need to be able to get to them. Some of these locations may require ladders to get to, just to put your hands on them. If you have a complex building with complex controls for the HVAC, you may actually need maybe not just the facilities guy, but maybe the mechanical contractor. And you need power for the test fans. This is easy to forget. Probably won't be as much of an issue in brand new buildings, but we do run into issues in older buildings sometimes. The fans draw enough amperage on startup that if you put more than one on a single circuit, you can trip the breaker. So as part of the setup, you should try whenever possible to have each fan on a separate circuit. Not always possible, but it's a really good thing to do. If you put two fans on the same circuit and you fire them up both at once, you may trip the breaker. Next slide, please. So double check your boundaries. Where are you testing? What surfaces? Inspect the geometry for interior barriers to good pressure distribution. This is an issue in single family, but not much. It can be much more of an issue in larger buildings, especially buildings that are fairly leaky, and especially buildings that are broken up into a lot of pieces. So if you think, if you're at the end of a long hallway and your blower door is depressurizing the building to 50 or 75 pascals at that location, do you actually have that same pressure difference across the rest of the envelope? The answer is probably not. I mean, maybe you do. Maybe you're testing a gymnasium where there's no interior barriers and it's very easy to get the entire space to the same pressure. But the more the place is broken up into little rooms and long hallways and convoluted passageways and narrow stairways, it becomes harder to get even pressure distribution around the building. So you want to think about that when you're selecting which doorways to put the fans in. You want them spread out as much as you can. In parentheses there, you'll see a kind of a rough rule of thumb that if you pull 5,000 CFM through a regular doorway, it'll drop a couple pascals across that opening. 5,000 CFM is about the flow of a blower door fan, almost maxed out. So you could see if you're trying to pull air from some place where that air has to go through like 3 different doorways before it gets to the fan, the pressure difference across the envelope out there is probably not as big as what you're measuring standing right there at the fan. So you want to be measuring the pressure difference between inside and outside, not just where the fans are, but also in the locations that you think you might not be getting good depressurization. And the standards by which we test say that if you want an accurate measurement, all the building pressures throughout the entire test area should be within 10% of your specified test pressure. So if you're measuring 75 at the blower door, there should be no area in the building that's any less than 65. And the only way you know that is to measure. So when you look at the geometry, you decide where your fans are going to be to get the best distribution of pressure as you can. And then you want to ask yourself, if there's a place where I'm not likely to get good pressure, where is that place? And put a pressure tap there. and measure the pressure between there and the out of doors to make sure it's within 10% of the number that you're getting at the blower door. And it is good to use multiple outside taps. You're probably going to do that anyway. I think it's a good policy if you've got blower doors in 3 or 4 different locations, just be measuring the indoor-outdoor pressure at all of those locations and record all of that. Next slide, please. How many fans do you need? This can be a head scratcher, but not for code compliance. For code compliance, all you have to do really is you have to know the surface area of the building or the volume if you're doing air changes per hour, but the commercial code is on surface area. So if you know the surface area and you know the standard that they have to pass, then all you have to do is do a simple math formula, and it can tell you that if they just barely meet that standard, that results in a certain CFM number. And we just look at that. So we know that that's the CFM that it will take to depressurize the building to the test pressure if the building is exactly right at the standard. So we just bring enough fans to do that. And if the building meets the standard, we will get to 50 pascals or 75 pascals, whatever we're testing at. So if we brought enough fans according to that formula I just laid out, and the building meets the standard, we will be able to get to 75 pascals. If we can't get to 75 pascals, the building will fail. And we will get a sense of how badly it fails, because even if you don't get all the way to 75, you can still get a pretty good idea. And we can extrapolate from, whatever test pressure we can manage on the building up to 50 or up to 75. We do that all the time in single family residential. So we like to, when we're testing for code compliance or meeting some program, we like the measurement to be as accurate as possible. We would like very much to actually meet the test pressure. But if we don't, as long as we're somewhere in the ballpark, we can still get a pretty good idea. And again, for code compliance, unless the building is right on the edge, we'll probably know the answer, even if we can't get to the test pressure. In other words, we may not have a super accurate number, but we will know what side of the pass-fail line they are on. So that's for code compliance. For ordinary construction, if you're doing existing buildings, here's some rules of thumb. So you're probably somewhere between 0.2 and 1.2 CFM per square foot at 75. And that translates to a leaky building. You want a rough rule of thumb, a leaky existing building, about 1 CFM per square foot at 75 pascals. An average building, maybe 2/3 of a square foot. And a new tight building, maybe 1/3 of a square foot at 75. So if you've got nothing better to go on than that when you're trying to figure out how many fans to bring, that's at least a rough approximation. Again, if you're doing just leak detection and you're not really all that concerned about what the number is, you don't need as many fans, because you can find leaks at 10 or 20 pascals. You don't need to be at 50. And also, rough rule of thumb, the Minneapolis blower door fans will move about 5,400 CFM at 50 pascals, or a little less than 5,000 at 75. That depends a little bit on your electric supply. It kind of assumes a good, robust, up to snuff power supply. Next slide, please. Hey, what should you bring? You should bring miles and miles of extension cord, because the outlets are going to be far away, and you're going to want fans on separate circuits. And you might end up putting 2 or 3 fans in the same doorway, which is in a hallway, and the hallway doesn't have any outlets. All the gauge tubing you own with the connectors, you're going to be running distances. If you only own 50 feet of tubing for your gauge, you should buy a couple hundred more. You're going to have to prop a bunch of interior doors open, especially if you're doing multifamily. So you need some strategy for that, a box of wedges. Masking tape, ducts, masks, garbage bags, tape, stuff like that. You want to have that on hand. Whether you actually use any of it depends on what the building is and what your purpose for testing there is. It is a good idea to have some cleaning stuff along with, just to keep from pissing off your customer. Some sort of communication for each phone. Door signs. If you have a door that needs to stay closed, but you know it's going to be unlocked, you might want to have some signs pre-printed to ask people to close the door. Or if you have propped the door open and you think some well-meaning person might close it because, they think it should be closed, you might want to have signs for that purpose. So 2 batches of signs, one that say, please keep this door open, and one that says, please keep this door closed. And if you got to reach the ceiling in a commercial building, you're probably going to need a ladder of some sort. On to the next slide. Just a quick look at 2 rigs. The one on the right, you probably won't end up using this one. It's made by Retrotech. This is a beast. It moves about 60,000 CFM, so it's about as much as 10 standard fans. You need an overhead door to set the thing up. It's a gas-powered engine. So I thought you might enjoy a look at that, even though probably none of you are going to go out and buy one next week. Some of you might consider buying the rig on the left, though. This is the Minneapolis Blower Doors 3-fan setup. This is not their current setup because you can see that they're using the older DG700 gauges. They're selling all their setups with the DG1000s now. So they do have a system. This puts 3 fans in 1 doorway. This gives you the capacity of moving maybe 17,000 through a single doorway. So not a bad way to go. They sell this entire rig as is with the gauges and everything. And if you take this to the job site and you're doing automated testing, you can do everything with 1 person. If you are only using 1 doorway. And you could even do it with only 1 person using more than 1 doorway, as long as all the gauges are Wi-Fi enabled, or if you're using Cat5 cable to the ones that aren't. So worth thinking that sometimes, for instance, the last time that our staff did a multi-fan test that I was involved in, we used 8 fans and 7 people. And it's expensive to bring 7 people to a job site. And some of these could literally be done by a single individual. On to the next slide. This is what that setup looks like if you're using the Cat5 cables. So on the left, you can see your laptop is, it goes to a specialized box that you get from those guys, and then a separate cable. And then on the right, you can see what happens at the other end of that cable that goes into the gauge. The gauge is hooked to the speed control on the fan. And with this setup or with the wireless setup, you can do the entire test from the laptop. With the one exception that you still need to physically remove the rings or perhaps put rings on. So the equipment has not completely replaced the humans quite yet. On to the next slide. If you are doing an automated test on your laptop, you have a choice between 2 modes of control. I don't want to spend much time on this. I'll just mention briefly that you can do manual control, which means you control each fan separately and manually. So you can turn on each individual fan, control the speed from the laptop. Auto control brings all the fans up together and makes some sorts of automated measuring a little easier. Next slide, please. And you remember I talked about those interior pressures. So if you suspect that you may have a problem with that, and again, this has a lot to do with the type of building we have, how segmented it is, how broken up into pieces it is. And basically, you just want to find the spot that is likely to have that kind of problem, that is too far removed from the fans to be well depressurized. Measure the pressure difference there and make sure it's within 10% of your test pressure. Next slide. How accurate does it need to be? I kind of touched on this before, so I move through this. You know, it depends what question you're trying to answer. If you're just finding the holes, you're just finding the holes. If you're just getting a rough idea, rough idea. We don't need a super accurate number there. Informally testing to a specified leakage rate, yeah, we would like a good number there, but you know, if it's off by 10%, probably doesn't change anything that we do. Certifying according to a specific testing standard, which is what you would do if you were testing for code compliance. There, we absolutely do want an accurate number if it's close. If the building is close to the line, we want to have absolutely as accurate a number as we can get. But if the building is an obvious pass, or if it's an obvious fail, then it's an obvious pass or an obvious fail, right? Next slide, please. Documentation is going to vary, and sometimes you will have a specific standard that says you're supposed to document stuff, but this is, as a practical matter, every single time you want to document this. What's the weather conditions? And again, temperature correction is something that a lot of blower door folks miss. They either don't know about it, they don't know how to do it properly, or they just forget. You want to be on top of that. Building configurations, what positions were the doors in when you did the test? The location of the blower doors, which doorways were there in? Did you have two fans in this door, one fan in the other door, etc.? What was the mechanical equipment doing? Was it on, was it off, or was it off and sealed off? And obviously, whatever numbers you end up with. On to the next slide. And I think this is the last one for my section. Just, you know, stuff does happen. You should know about the spinning the fans backwards thing. If you're using multiple fans in the same space and you turn one or two on first, but you don't turn the other ones on yet, the ones you turned on will depressurize the space, and that will cause the other fans that are off to spin backwards. This is not good, because if you turn the fan on when it's spinning backwards, there's a chance it could reverse if it's not spinning very fast, and then you're okay. There's also a possibility that it won't reverse. It will continue running backwards, and sometimes it can be surprisingly hard to know that that's happening, because you've got other fans operating in the space. The pressure in the space doesn't necessarily reflect what that individual fan is doing like it does usually. And it's surprisingly hard to know that it's still spinning backwards. So that might happen. The other thing that might happen is that the fan might blow up, and that's not good. And, you know, occupants open things, they close things, they turn things on, they turn things off. So it's good to have good communication there, good signage. Things get unplugged. Sometimes we have electrical service issues. You probably won't have a problem in new construction, but in existing homes, we sometimes do. If you're using Wi-Fi, you may have signal issues. If you're having to mask things off, you know, sometimes you may blow the masking off because it wasn't adhered well to dusty surface or whatever. And like all testing with blower doors, the wind can be a problem. And I think that's, oh, one more. Yes, here we go. So two resources. One is the Energy Conservatory and one is Efficiency Vermont. The Energy Conservatory does do a class on this. It's a 2-day class. They typically offer it a couple times a year at their location in Minneapolis. I think it's still free. So you basically have to get yourself there and grab a hotel room, but they'll do the training for free. And they also have some written stuff about testing big buildings that's on their website. They have a lot of good information on their website. And if you are a home performance contractor or a building performance contractor and you need a little help getting going on this, you need a little on-site assistance, either with advice or training, or you know, this building requires more fans than you own, feel free to call Efficiency Vermont, and you know, we're kind of informal about that, but we will help you as best we can. And I think that's it for this section.
Hi, everyone. I'm Karen Bushy. I'm going to be talking a little bit about air sealing opportunities in commercial construction and covering both new and existing assemblies. You can go to the next slide, please. So As we've heard quite a bit already, there are a lot of variations in commercial assemblies out there. There's everything from steel construction, hybrid steel and concrete, all concrete, and even wood frame construction that is similar to what we might see in residential. And with these each come a wide range of air barriers, locations, types, and also vapor barriers and thermal barriers. And even, just knowing where the air barrier is, it can be really a challenge. All of these systems have different ways of dealing with that, or they might possibly not deal with that. So uncovering that is kind of our challenge. In addition, you might see a wide range of qualities of installation, which I'll get into some photos of examples as we go. And there's lots of factors here to consider in making a building more airtight. You can go to the next slide, please. But the most important consideration in the air barrier is that it's continuous. Here is a method that's often used in new construction or even deep energy retrofits where there's a detailed drawing set done where you can actually do sections of the building and follow that air barrier through with a dashed red line or any color you want, really. And what this is doing is this is helping the design team, first of all, delineate which material is acting as the air barrier. And it is also helping them see all of those connections and intersections and follow it through each of those. And then you can go in and enlarge each of those transitions to look at exactly how the air barrier is making that transition and moving from material to material. Next slide. So then when you dive into those details and enlarge them, you can look at that with even more of a fine-tooth comb and understand exactly what material that is, point that out to the construction team. It allows you then to review this in advance. And this particular project actually did an amazing job, which is why I wanted to show it as an example of delineating, not just the air control layer, but also the vapor retarder, and maybe when those are possibly the same material, it delineates that in yet a different color. So it was really helpful to very visibly draw that out for the entire project team. One of the things that this project team actually mentioned was a lesson learned was sequencing. So in new construction, you're starting with a whole series of, structural systems first. Well, obviously foundation and site work, structural systems. And so each of these barriers kind of takes place in a different phase. And there's different aspects of that might be built at different times of the project due to needing that material to get in at a certain time, or else you won't be able to access the area where it's to be installed. So I've even heard of teams doing 3D drawings of the different systems layered on top of each other. And it's actually a really useful tool to work with the design team and the construction team to be able to just dive into those areas and look at the layers of materials as they get constructed. One thing I wanted to point out also with the red line air barrier is, you don't have to go back, but just that's also a good opportunity to calculate your envelope square footage, because that can actually vary pretty widely in commercial construction. Even if you may not even know exactly where it is, it can be just a puzzle in itself trying to figure out where your pressure boundary is to take this calculation to be able to accurately calculate what your CFM 75 per square foot measurement is. So even if you don't have drawings of the project, just like a quick hand sketch of what you think that section looks like, and could have a couple of different possibilities of where that air barrier is, and maybe change your mind as you go along with your testing, but all options. Next slide, please. So this is the same project. What you get when you do really detailed air barrier drawings like that is, this was a pretty early preliminary blower door test, and they didn't even have the windows or doors in yet. So what they found in the leaks were not any of those areas that were heavily detailed and heavily, commissioned and had a lot of eyes on it. What they saw for leaks were actually the penetrations and the missed mechanical conduit and the mechanical penetrations and the connection to the existing building, which this project has. All of those kind of like easily missed areas are what you end up, where you end up seeing the leaks in projects like these, which is a good sign. Those are, at least, at this stage of the project, those are easy to see and easy to catch and easy to fix. Next slide. So I'm going to just dive into a couple different sort of categories of areas of, looking for leaks. This is somewhat more typical if you're used to residential or wood frame construction, but we also see it plenty of time in commercial construction and some version of it in historic commercial construction. This is notoriously one of the biggest areas for leakage. So a really good area to look if you're doing a blower door test to sort of investigate for leaks is the rim joist. There are lots of opportunities here for air to enter in several different places in this assembly. If you're lucky enough to have access and you can see the underside of your floor system from the basement, then you'll be able to easily tell where those leaks are coming from using either an IR camera or even just your hand. If it's really leaky, you'll probably feel where those are coming in pretty easily. If you have a situation where you have a finished ceiling on the basement, then you might be looking for something more like what you see in this upper picture right under the title, where the infrared image is showing kind of the fingers of the air leakage coming in through that sill or rim area. And that would be an indication that you might want to demolish a bit of the ceiling there to really get in and see what's going on. A couple ways to deal with this, to remedy it. What we see very frequently in residential construction anyway is closed cell spray foam at this area, because it's doing both air sealing and insulation in one pass and pretty effectively. The most important aspect of that is to get that foam continuous from the underside of the floor deck all the way over the top of your foundation wall to seal that entire, all of those joints. Other than that, if you wanted to avoid spray foam, there are definitely other options. There's caulk in the traditional sense. And then there's kind of a sprayable caulk that's an option. And there's also a sprayable or paintable air barrier material. There's several out there now that are pretty easy to come by, that are safe for interior application. And that's a nice way to be able to quickly do your air sealing, and then you just have to follow through with your insulation material after that. Hopefully you'd be going that route. Next slide, please. Here's an example. If you have, this is new construction. The first couple examples I have here probably pertain more to new construction. This is not something that you would see in maybe your typical code level new construction building for slab on grade. This is actually a passive house project, or a couple pictures from multifamily buildings that were aiming to meet passive house airtightness. And that looks like something more like the picture on the bottom right, where you'd have a complete continuous subslab vapor barrier also acting as your air barrier, with all seams taped, all penetrations sealed. And that air barrier then continues out over the top of the foundation wall, and the exterior flap of that gets folded up and taped to the outside of the sheathing, therefore completing that continuous air barrier. And that's exactly what I was talking about when I was mentioning diving into those details and really looking at how the air barrier is transitioned from plane to plane and material to material. But if you had something more traditional, like either existing or new, just your bottom wall plate sitting directly on concrete or on the slab, then the most important detail there ends up being that transition between the bottom of the wall plate or the sheathing, if that's your air barrier, and the concrete. And there are lots of ways to deal with that. There are gaskets that you can put between the bottom plate and the slab. You know, you can literally just caulk those joints if it's existing construction and you can't get in any further than that. Tape the sheathing to the concrete outside. There's lots of options. Next slide. So the same kind of details also apply to openings. This slide sort of applies to both window, door, and penetration openings, like mechanical penetrations or electrical in the outside in your exterior wall. Using tape, there are kind of different ways that you probably want to look at approaching air sealing, and a lot of it depends on what your air leakage target of your project is. If you have something in the realm of 1 CFM 75 per square foot in an existing building, and you're trying to have that to 0.5, probably doing foam at the edges of the windows and any penetrations would be fine. You know, you'd probably be lucky if you can get to all of those areas. You might only be able to do that in a deep energy retrofit. But if you're trying to meet 0.05 CFM 75 or 0.06 or even 0.08 for the passive house standard, then you're probably looking at using tapes and even gaskets for a lot of those transitions around openings and penetrations. Next slide. And then moving on up to the roof or ceiling level. These are pictures of new construction examples, which, you know, in those situations, it's a lot easier to get to all of the seams in your drywall. If your ceiling drywall is your air barrier layer, which turns out often to be sort of the cheapest and easiest location to put it. A really effective way is just sealing all of those seams and penetrations and light fixtures and fans, anything that's going through that ceiling layer, just sealing it from above with either caulk or foam. A lot of the same kinds of materials can be used that I showed in the rim joist example, or you can use a continuous membrane. There's a whole bunch of different smart vapor barrier / air barrier membranes out there that do a couple different jobs and are really effective. So you have a lot of options there too. I think I have more on the next slide. So next slide, please. Right, okay, so here's an example of specifying a certain material to do that job of the air barrier at whatever layer really. It doesn't necessarily guarantee success, and there's a lot of work that goes from the specification and the detailing of that and follow through all of the construction sequencing and schedule to ensure that you're meeting your leakage target at the end. You can advance, please, Tori. So in this example, the project team specified this smart vapor retarder, which seemed like a great idea at the time. And we weren't really thinking it through and realizing that this is actually the ceiling that we were dealing with, which made it extremely complicated. And there's some more to this. So you can go to the next slide, please, Tori. So there were even interior framing walls that needed to be in place for the structure before that this idea of the continuous ceiling, air barrier wasn't actually so continuous. We ended up having to specify that they put strips of the air barrier material on the top of these walls and then connect to them later. And you can keep advancing, Tori. There's a couple examples that follow. You can just keep going through them. So that's how that ended up turning out with all the tucks. And then there were just complications left and right in this project. There were truss ties at every truss that ended up creating these little gaps. And then this project was aiming for 0.05 CFM 50 or something closer to 0.08 CFM 75. I haven't done the final test yet, so I'll let you all know how it turns out. But it didn't end up turning out like we had all envisioned in the planning stage. There were some a lot of mechanical work that had to happen after that air barrier went on. So just holes left and right in this air barrier. Okay, you can go on to the next slide, please. This is an example. There are a couple staff at VEIC who were lucky enough to get to go out and test an existing school in Vermont and found some interesting things with the blower door test and IR imaging that went with it. This school was, I guess, cobbled together a lot of different types of construction, but this area that you see in the upper left photo is CMU block or concrete block with a corrugated or fluted metal deck just literally sitting on top of it. And you can see in the corresponding image to the right with the purple what happens when you do that and don't seal that edge. So I was told that the temperature outside at the day of testing was about 15 degrees, and you can see in that IR image that's exactly the temperature that it's reading. So that outside air is coming straight in through those seams. A great opportunity and very easy to spot with this blower door testing and IR imaging to go with it. If you can see the bottom of the roof deck, similar images just below that where you can actually see that roof to wall transition. If you have a situation where you have a dropped ceiling under that and you can't really see what's going on, and you're still doing a blower door test with negative pressurization, so specifically in the winter or cold temperatures when you can see this temperature difference coming in, a good thing to look for would be a pattern like you see in this right photo. This photo is showing what's happening above that dropped ceiling that we can't see. So just showing that cold air, that 15-degree air being pulled through all of the seams of that dropped acoustic tile ceiling. So if you were to see something like this in your IR image, this is a good indication that you want to demo part of that ceiling to be able to get up in there and see what's going on because you have a significant leak. Next slide. This is not our example, but I really like this example. It's a study that was done of some new commercial buildings in Minnesota that shows you that even in new construction, this kind of thing still happens regularly with the corrugated or fluted metal decking. It's a very, very common area to see leakage. And in this project, they were able to find that using IR imaging, and they were able to seal those up with spray foam. You can see in the lower right image. Next slide. Here's an example of an older historic building that was in various levels of disarray, I guess, when the project started. You can see an existing photo in the attic on the upper left. A lot of things, this was an older historic building. A lot of things were kind of put in place over time and added to the building. So there was a lot to work around. And it turned out that the best way to deal with the significant leakage that was found and bringing this building up closer to current code was to do spray foam. So there was quite a bit of spray foam used on this project. You can see in the pictures to the right on the underside of the deck and the basement, and even in the attic, which I don't have a finished picture of, but they did a flash coat over the whole bottom face of the attic and then added cellulose on top of that. It was extremely effective in cutting the air leakage of this building. It worked really, really well. There are different thoughts right now about using this quantity of closed cell spray foam. It's one of the insulations that has the highest embodied energy compared to any other insulation you can use, and has a pretty significant global warming imprint. So some folks are trying to move away from it, and if that is the case, there are other options. You can go to the next slide. This is a product, actually I think the same product as what I was showing in the rim joist example, that can either be spray applied or brush applied, and it's an air barrier material that can be applied. This is a great example of it because it's just applied directly onto the face of masonry. They're actually using part of the plaster in this project and just keeping it in place and keeping that as part of the air barrier too, to try to minimize the quantity of the product that they're using, which is a great idea. And this allows, you have to do it in 2 steps. You're doing your air sealing with this product, and then you have to add insulation separately if you need to add insulation at that location. But it allows you to do really effective air sealing without using spray foam. Next slide. These are just, whoa, we're really running out of time. I'll just try to fly through these a bit. We see quite a few metal buildings in Vermont, so I wanted just to point it out. If you're not familiar with them, they're built a lot like this, with kind of like steel. It's all metal frame construction, and then the insulation is drape and squish or sag and bag and just layered over that steel framing, and at those girts and purlins, it ends up getting squished, and therefore the thermal qualities of the insulation is actually compromised there. But that is how it's done, and sometimes you might end up seeing ice damming as a result. You can go to the next slide. What happens? So that insulation sometimes has a bonded vinyl vapor barrier, and it sometimes has a separate vapor barrier. In these cases, you'll see that they added just a poly vapor barrier under it. The reason I keep saying vapor barrier is because that's what they call it. They don't actually make a note at all in any of the metal building literature that I saw anyway about air barriers. So this vapor barrier ends up becoming the air barrier by default. But it's not really treated that way. So it's really a huge opportunity for these buildings, both new and existing, because unfortunately, we just don't see a high quality of installation in these buildings. These are pictures from a new building, I believe, all of these. Yeah, so you can see their entire sections missed of insulation, and in huge sections, there's a discontinuity of the vapor barrier or air barrier. So even just a big opportunity here would be to complete those areas and tape the rips in the air barrier and connect those to the exterior walls as much as possible. Next slide. And in new metal buildings, this vinyl vapor barrier, which is also the air barrier, is simply just attached to the bottom plate, typically. And then that connection between the bottom metal C-channel and the top of concrete is just not really dealt with at all. So that's another opportunity to either add a gasket there or caulk that joint, or dress it from the outside. And then at window openings, which we do see quite frequently, there's an opportunity also to connect that vapor/air barrier to the window. If you have a wood stud as you're blocking, that might just happen naturally with the sealant around the window rough opening and the barrier attached to the wood. If you had a metal stud there, you're going to need an additional piece of material because the metal stud by default has lots of holes in it. Next slide. And then some thermal opportunities. As I mentioned before, that insulation is typically installed with very little thermal break in there. And they have some additional details of ways that it can be done with a little bit more of a thermal break. The picture on the upper right shows a 1/8 inch foam strip that is used frequently as the thermal break. I mean, it has like an R1, so you can do the math. Another option for walls would be a exterior metal insulated panel, which are pretty neat. It's obviously an added cost, but it has air sealing built into it. As you can see in the picture right in the image right below the photograph, there's actually a joint that snaps together, and there's a nice channel in there to install the sealant while those panels go together. So they do air sealing and insulation in one. They come in thicknesses up to 6 inches. You can also do a continuous rigid insulation roof on top of these instead of the drape and squish, which definitely helps with the insulation issue. But if you do it that way, you have to make sure you're also thinking about it as your air barrier because the thing I completely forgot to mention before was these buildings don't have sheathing, which is the thing that makes it so hard to air seal them. So you're always looking at another product to do that job of the air sealing. So the rigid insulation on the roof would want to have all the seams taped, and it would want to address the end condition of the roof to wall. Next slide. I'm going to kind of skip this, but just going along with the idea of the thermal envelope. If you have your ducts outside of the thermal envelope, you're probably going to want to do something about that, because that's likely a lot of your interior conditioned air that you're losing. Next. Okay, so I'm just a little bit about compartmentalization. We can actually skip this because I think Dave went over this pretty well. So I've done quite a bit of multifamily unit testing the last couple of years, and the current requirement, or the requirement that's going into effect in September, of 0.35 CFM 75 is going to be a serious challenge to meet in typical multifamily projects. So I just wanted to say a little bit about that. I'm doing a lot of testing lately for passive house compliance, which requires a 0.30 CFM 50 per square foot of envelope of the apartment. And it's been a serious challenge. A lot of the areas that we see, we see details like this to start with. We see drywall going to the underside of the deck. We see a real investigation into understanding where that boundary, where the pressure boundary of the unit is, and following it all the way through. We see pressure. We see vapor type electrical boxes. And then some of the areas that are easy to miss would be duct chases, electrical chases, because there is an opportunity to bring a huge amount of air in from neighboring apartments. Next slide. Okay, good. So I guess what we really want to say in the end is, there's a lot of different situations that you might run into out there, and we'd like to help in any way we can. So please contact us. And that is it.
Thank you, Karen, and thank you, Dave and Charlie as well. We have just a few minutes for questions. So if there are any questions that folks have, you can submit them in the chat. And yes, the slides will be posted. This presentation is being recorded, so the recording will be posted as well. Give folks a moment to type any questions that they have. I think we had one about ventilation, but it looks like that was answered in the chat. All right, well, if there are no other questions, I think we can go ahead and wrap this up. So thanks everyone for joining us today, and thank you to all our presenters. And have a great day.
Thanks, Tori.
Thanks, everybody.